as opposed to our physics. All right, let me tell you the plan for the day real quick, and then we'll jump in. It's going to be a pretty low-key day, I think. First of all, just a friendly reminder, the reminders are going to be the same for a long time here, friends. Make sure you wash your hands, okay? Always, all the time. Make your hands all dry and cracked and gross, and then get some lotion, okay? Wash your hands all the time. All right, today's plan, we're going to do a quick warm-up problem together, and then we've just got a bunch of problem solving to do today. Today is our last day of uniform circular motion problems. We're going to do, tomorrow is our lab analysis from the lab that we did last week. Okay, so that'll come up tomorrow. We'll do that. And then we're going to move on to some applications, other applications of uniform circular motion. So this is like kind of our last big hurrah of this. So we're going to do a problem. I've got a bunch of like problems for you to work. It's just going to be kind of a work on problems kind of day today. Sound okay? Sweet. All right, so we got to start with this warm-up problem because that's, where we start for these things. So here it is. A block on a string spins in a horizontal circle. So that means that we're going not this way. That would be vertical, right? Like when I did the cup with the water, that was a vertical circle. Horizontal means like this on a frictionless table. So this is kind of like the yo-yo on the floor. That's what we're talking about here. Rank in order from largest to smallest. The tension in the string acting on block A to block E. So it gives you not only the radius of the circle, but also the frequency. What does RPM stand for? Revolutions per minute. Yep. All right, I'm gonna let you go ahead and get started. An answer. Will you write it on the whiteboard so that I can see it, so that we can kind of compare? Would you do that real quick? Just throw your answer on the whiteboard so we can take a look. I'm just gonna write them down just so we have something to start from. So I see E is greater than C equals D, greater than B equals A. That's one board. I need more boards. Show me your boards. We have E greater than D, greater than C, greater than B, greater than A, E, D. Okay. Whoa, that like the enthusiasm there is like a little bit something. Do you guys agree with that? Okay. No, here's the thing, is I was looking back at my notes from last year. These are the exact same two that they had last year too. And probably about half of the kids had either one. So here's the thing, friends. You know how I roll. Is it the right answer? I don't care. Is it good physics? That's what she cares about. That's what she wants to know. So I need you to talk me through it. And the reason I want to do this is partially because I want to make sure that we all know the right answer. But it's also partially because when I was talking to you, some of you, even if you got the right answer, did a whole lot more work than you necessarily need to do. And I just want to remind you, as you're getting closer and closer to the AP exam, that looking at these things and trying to be a clever problem solver can sometimes save you a whole bunch of time. Does that make sense? Because a problem like this, it probably wouldn't be quite this intricate in terms of like rank all of these, but something like this totally could be on an AP exam, right? As a multiple choice question. I would not be shocked to see something like that. So let's talk through the physics that goes with this to make sure that we really get it. So can somebody start me off here? What did y'all do? Where'd you start? Autumn, can you start us? Where did you start the conversation? Yes, we did. What was it? Okay. Sweet. Do you want to say more about that, or is that? Say one more thing. You're good. Okay. Okay. And so you kind of chew on those things and put them together, right? Absolutely. How many other people started there or used that at some point in their process work? Yeah, it's there. That's exactly what we want to do. Now, this question isn't really asking for a centripetal acceleration, though, is it? What is it asking for? The tension. So we need to get tension into this story. How do we fit tension into the story? Chris, how do you fit tension in the story? It does indeed. F equals ma. And I've got A, so I could say this is equal to F over m. Is that okay? Okay. And so if I know something about A, I can tell something about F. And is there any, do we care about M? No, because they're all the same. So we're all good. So really, if we can rank, this is the thought process I just want to make sure we're articulating here. If we can rank the accelerations, we can rank the forces. Okay, so let's rank the accelerations. And Autumn, you said that we can't, I mean, we don't know any V's, but we do know something about V, right? Somebody else help me out to figure out V. What are we going to do? How do we figure out that tangential velocity? What's that? We do need the circumference. How do you find the circumference of a circle, friends? 2 pi r. I don't know why things are disappearing on me there. It's kind of creepy. A sub c. Okay, so if we know that, that's just the circumference. That's not the tangential velocity though, right? How do I find tangential velocity? I know the circumference. What else do I need to know? Yeah, the amount of time it takes. So I'm reminding you of all this because, whoa, hello. Because this is basic. This is back from like day 2, right? And then if we think, okay, well, we're going in a circle, so it's 2 pi r. And then we have to divide by how long it takes. And this is a pretty fundamental way to look at this. But they don't tell us any t's here, do they? Jerks. But they do tell us f. How does f relate to t? It's the inverse, right? So instead of writing 2 pi r here, I could write, or to me, 2 pi r over t, I could write over 1 over f, which is the same as just multiplying by f. Is that okay? Awesome. All right, so I've got 2 pi r f. Now, that might seem kind of funky. You can also think about this if you wanted to go from the angular route. You could say omega is equal to 2 pi times f. We did that a long time ago, right? And then you multiply by r to get to the translational. That works as well. If that is how your brain is working now, fantastic. Absolutely. Yes. We can say that omega is equal to 2 pi f. That comes back from the rotational stuff that we did a while ago. And then I know that v is equal to omega r. So that means that it's 2 pi r times f. It's all the same deal. So the reason I wanted to show that to you is that you can come at this from different angles and it all works. It's all good. There are lots of ways to approach this question. Okay, so we know that v is equal to 2 pi rf, and we know that a sub c is vt squared over r. Have we plugged any numbers in yet? No, that's cool. We don't like to plug numbers in until we have to. All right, so a sub c is equal to vt squared over r. So we can say a sub c is equal to, this is 2 pi r f squared over r. Can we simplify that at all? One of the r's, right? Yeah, one of the r's on the top and bottom. So we can say that a sub c is equal to, so this is 2 pi squared, whatever, we don't care about that because that's all constant, rf squared. All we care about is what? These two little guys here, right? And which one matters more, the r or the f? The f matters more. You with me there? There's a lot of physics that happened here without doing anything with these numbers. Then you can just square your frequencies, multiply by r, and you can get this quantity, right? The other reason I wanted to go through this part of the process with you is that sometimes the questions on these kind of questions on an AP exam, they'll give you extra information, right? Maybe they'll say that maybe they want you to rank the accelerations, but they give you the mass. Do you need the mass to rank the accelerations? Indeed, you do not. So you need to make sure you can kind of like know that, so you don't just arbitrarily start multiplying numbers together, right? Because that can get really dangerous and we don't want to do that, okay? So I think if we actually work through all of that, does that get us to this rank here? Okay, okay. But again, I want to make sure that you know how to get there from where we started. Questions that you have so far? All right. So I've got 2 little cute sheets of paper. They're really cute. They've got some problems on them for you to work. So I've got a set of yellow ones, and then I've got a set of green ones. We're going to do the yellow ones first. And I'm just going to let you guys work on these. I was telling Mr. B, because, you know, when we're not doing class, we're talking about like how to teach and pedagogy and all of this sort of thing. And we did something very similar to this with my big physics classes. We did this kind of like organized, like jigsaw thing. And then we're talking about, do we do that in here with you guys? And I feel like you guys are okay to just work problems. Is that, are you feeling like that is a true statement? Chris, are you feeling sad? Did you want to jigsaw things? We can totally do it if you want. If you're interested, come over here and we'll figure out how to do that. Really, I just want you to understand how to do these 3 problems. And then I've got 2 more for you after. That sound good? Okay, so why don't you send somebody up? If you want to just work these on a whiteboard, so you just start because whiteboards make your heart happy, do it. The only trouble with that is that then you don't have them long term to look at them again. So you can take a picture. If that works for you, awesome. Come up and get those problems. What did you whisper at me? Hey friends, let's have a physics conversation real quick because we can and we might as well because learning is a great thing. Who said oh? What's wrong? All right, this is the right one, right? Yeah. Okay. So we got to figure out what to do. A 2,000 kilogram car rounds a corner of radius 45 meters. The coefficient of static friction between the tires and the road is this. What is the greatest speed the car can have as it rounds the corner without skidding? So what are we going to do? I don't know. When I am dealing with a forces problem, the very first thing I ever do, even before I write down my givens, is what? Free body diagram. Now, there are different ways that you can draw this free body diagram. You could draw, I mean, it's probably not a whole, like, here, hold on. Let me try that again. So it's probably like a curve like that, but it's in the middle of the curve. So here's the car. I'm looking at it from above, right? I'm like on an airplane. Here's my car. And as it's traveling, it's got gravity pushing in, it's got normal force pushing out, but I'm not worrying about those right now. What else is pulling on it or pushing on it? Friction, right? If you had the opportunity to drive it all during the snowy, slick, nasty parts of the winter, right? You know that it is friction when it's there that keeps you going in a circle. If there is no friction and you're going around this curve, you're going in this direction, let's say, going around this curve, if there's no friction, where do you want to go? Say it loud, Lucy. You want to go tangent, right? Because you're an object, you want to go in a straight line. There's no reason to not go in a straight line. Let's go in a straight line, please. So you want to go like this, like that. This is that's your tangential velocity. That should not actually go on a free body diagram, but that's tangential velocity, right? But luckily for us, it's not super icy out today. And in fact, that friction can keep us from going in a straight line. Which way does that pull? Which direction does the friction pull? Opposite what? So the friction pulls this way. Oops, hello. The friction pulls this way? Is that going to keep it going in a circle? The friction is the thing that's going to keep it going in a circle. So if it's keeping it going in a circle, it's uniform circular motion, which means that it's got what kind of acceleration? Centripetal acceleration, which means there's got to be a force pulling which way? Towards the center. Yeah. So sometimes, and this is why we do these problems, we know that there's friction of the wheels going, that's kind of like, slowing you down. But thank goodness there's also static friction keeping your car, if I'm driving this way, keeping my car from going this way or this way, right? Thank goodness for that. We've got to have that friction. It's pulling you in towards the center of the circle. Okay? If I look at the car like head on, so there's the road and here's my car and there are my little wheels and I'm driving, let's say I'm driving out of or into the board, okay? Now I can draw it with the rest of my forces. So I've got the force of the earth. I'm just going to draw these fast, FG, and I've got the normal force. How did the force of gravity and the normal force compare? Equal in magnitude, right? And then, so I'm kind of drawing it from this way, and my friction is going to go, so like, let's say that the curve, like you can't, I'm not good at drawing like artsy things, but that's kind of what's going on here. The frictional force is pulling this way, FF. That's the thing that's keeping us in the circle instead of driving off of the road and into the ditch. And then you have to call your mom. Mom, help! Right? That's what we're talking about. Thank goodness for the friction. Yay. Okay? How are we doing? Whenever you're doing these uniform circular motion problems, you got to figure out what the forces acting are, because if you don't know that, you really can't solve the question. Okay, you really can't do it. Once you've got a free body diagram, then it's pretty easy to write your your F-net equations. So we can write F-net in the y direction. We can write F-net in the x direction. What forces are acting in the y direction? Fn and Fg. I like doing this at this point in the year because it's been a while since we've been doing this, right? Got to get back in the good habits that we had before. And that equals, are we accelerating? No. So MA is 0. In the x direction, how many forces do we have acting? Just one. If we've only got one force, are we accelerating? For sure we are. And in this case, we are accelerating going around a circle, which means our acceleration is what kind? Centripetal acceleration. Yeah? From here, see if you can jump in and play. All right? I'm just going to mention here in the second question. The second question is very similar, but it asks if the car will make it around the curve. So in that case, we have to think about the fact that friction, this is static friction. Remember, if friction is less than or equal to, so we're looking for the maximum friction it can provide to allow this thing to go around the curve. Okay? Well, let's keep working. That's fine. I'm not going to judge you. This one's a little bit funny. So for those of you that have ever driven a car, I don't know if you've noticed, but usually the curves that you drive on are not flat. You ever notice that? They're a little bit banked. And the reason for that is because it's icy in Iowa. And because there are times when the coefficient of friction goes down to nearly 0, and you need to be able to go around a curve even if there is very, very little friction. So we use the normal force instead of friction to keep us on the road. Okay, so just like with everything else, first thing we're going to do is to draw a picture. Okay, so this says if a roadway is banked at a proper angle, a car can round a corner without any assistance from friction between the tires and the road. It says to find the appropriate angle for a 900 kilogram car traveling at 20 meters per second in a turn of radius 85 meters. So we can draw that same bird's eye view picture, but the bird's eye view picture is going to be very similar. We just need something pulling in. So I'm going to go ahead and draw the picture from the side with a, it's kind of like a ramp, you guys. It's like we did these a long time ago. Welcome back to, some ramp problems. Hello. Here we go. So here's my road. Banked at a pretty severe angle. So this is I'm not driving up the road. I want to make that clear. I'm driving up this way. This is, I'm driving into or out of the board. Okay. So my car is right here. All right, like here's the top. Here is my person driving the car. Okay, does that make sense? So there's like my little headlights. I'm driving into, or I guess I'm driving into or out of the page right now. Okay. What forces are acting on my little car as it's driving out of the page? Force of the earth. Which way is that pull or push? Down, straight down towards the center of the earth, right? So it's going to go straight down like this. FG. I'm going to go ahead and mark that angle theta so that I know that it's there. Oops, that's really kind of a goofy looking theta. Okay. What else is acting? What is it? I heard somebody whisper it. What'd you say, Lucy? FN, she says. Yes, indeed, FN is acting. Which way does FN act? Perpendicular, right? Normal means perpendicular surface. So it's going to come up like this. Okay, here's my FN. Okay, now, every other time that you have done a angle problem, or excuse me, a ramp problem, we always break FG up. You remember this? Break FG into its parallel and its perpendicular parts. Okay, not today. We're going to switch it up because this car is moving in a circle. And the circle that it's moving in goes this way. You with me here? Okay? Gravity is not pulling it in towards the center of the circle. Part of the normal force is pulling it in towards the center of the circle. So we're mixing things up a little bit, and we're going to break Fn into two pieces. Okay? We're going to break Fn into a piece that goes straight up. I'm going to call this Fn in the x direction. Might be a little bit long, but you get the idea. And I'm going to call this one Fn. Oh, I said that's on the x direction. Why didn't you guys say anything? Jeez, that's embarrassing. And you let me say it out loud. Gosh. This is Fn in the x direction. Jeepers creepers, you guys. How are we doing? Are we okay? Whoa, hi. There we go. Oh, it's gone though. Let me do it again. I feel like my computer is ready for it to be spring break now. Oh, there it is. See, it just like showed up again. I don't know. Anyway. Fnx is the thing that's pulling it into the center. That is the force that's causing the centripetal acceleration. Fny and Fg should be equal in magnitude opposite direction so that the car doesn't into or fly off of the road. Okay? So when you write your F net equations, you're going to have one in the x and one in the y. All right? I'm going to let you play from there. Does that sound okay? Okay. You got a few minutes. You got some time. You got this.